Next, we have the best of abstract interpretations by Roberto. Speaker is Francesco Ranzato. Yeah. Okay. Yes. Okay. And at least one guy has.
Okay. So we are speaking about abstract interpretation, of course. What is the setting? The setting is that we have an abstract domain. Yeah, it works. Abstract domain means that we have an abstraction, we have a concretization, we have an operation. It can be thought about its transfer function and the corresponding abstract transfer function, as depicted by this diagram. So we need soundness. So we need transfer functions which are correct approximation, and that means that this inequality must always hold. And so what happens is that here we could have an imprecision between this function and what happens for the abstract function. When this imprecision shrinks to 0, what we have is an abstract function which is the best Cauchy approximation. And so the best is the motivation of the title. We study this best Cauchy approximation, which are very well known. So this is for transfer function. This is the notion of being best for an analysis. So the analysis means that we do all the computation here for the analysis with respect to what happens in the concrete semantics of the program. And so we say that an analysis is the best one locally to some precondition, A, which is an abstract value, when it happens that we do the best we can do. And so it's the abstraction of the concrete meaning of the programs. And then we define what is a global notion of being the best when this happens for all the possible abstract preconditions. Okay, so which programs do we consider? Standard programs. So the syntax of our program is given by the usual clean syntax, let's say. So we have basic commands, typically assignments and Boolean guards, but it could be anything. Compositions of programs, sequential composition, choice, and iteration as given by the clean star. Semantics is standard. So let me just point out composition is composition of functions. Choice is the union, disjunction. And the clean star is iteration for any k. So we do analysis, and so we have a corresponding inductive definition of abstract semantics, and we are interested in studying when these best notions happens. And so we start from the interpretation of the basic commands, which is the best we can do. And so the definition for the basic transfer function is that we need to consider their best Cauchy approximation. And then the definition is the usual one, the inductive definition. So here we have the list upper bound for the choice. Here we have the composition of the abstract transfer function. And then we take the loop of all the power of our program that we iterate. Yes, so you see in this definition there is no widening because the widening cannot be taken into account because there is no notion of best widening. And yes, here in the background you see a very simple example of a naive legal widening where you preserve no information at all. And so, yes, widening, of course, jeopardizes the property of being the best, and so it's not considered here. But it's not a limitation, it's a feature of considering the best. So what we know about BCA, being the best? We know that we know already that choice is not a problem. So if we put a non-deterministic choice between two programs, and we know that these two programs already satisfy the BCA property, then their conjunction, their disjunction, their non-deterministic choice still satisfies the BCA. Of course, this is not true for composition and iteration. Let me show a very simple example that BCA is not compositional, so sequential composition does not preserve the BCA. So first we do the +1 for some variable, then we do the -1, in which domain. The simplest domain we consider here is the sign domain. Okay? So locally to the first assignment, we are the best if we start from being positive. Being positive +1 is positive. Okay? So this is the best. Then we do -1, and -1 of being positive is not negative, and this is the best we can do. But this is not the best analysis of this program, because this program, of course, is nothing else than the identity. And so when you start from being positive, the best you can answer is you are still positive, which is not the same that you get by combining the two abstract transfer functions that compose this program. Okay? A second point that this example shows that, of course, abstract interpretation is inductive. And so the analysis of a program depends on how the program is written. That program, +1 followed by -1, is the same of the skip. And so if you have a kind of magic wand for transforming this program into this equivalent program, here you get the best analysis you can do, but not in this case. Okay? So in a sentence, in a slogan, this means that abstract interpretation is an extensional technique for doing analysis. It depends on how the program is written. And so this implication does not hold, of course. If you have two equivalent programs, it's not true that their analysis is the same. And this is a major source of imprecision when doing analysis, very well known. Okay, so which question did we study in our work? So first we try to answer this question: what is the relationship between this intentionality of abstract interpretation? So, okay, you know that for us AI is not the popular AI, but it's our AI, so abstract interpretation. So what is the relationship between the intentionality of AI and this lack of compositionality of BCA? Second question, I think natural question. So we have a program, we have an abstraction. Probably the analysis of that program on that abstraction for some input is not the best. And so the natural question is, can we manipulate the domain, so minimally refine or minimally abstract the domain in order to achieve the property of being the best on this transformed domain? And then finally, we ask the following fundamental question. So we have a program, we have an abstraction. Can we decide if the analysis of that program on that abstraction is the best? Okay? If this cannot be done, can we at least prove in a sound way that an analysis is the best? And so this is what we studied, and this is what you found. The answers are found in the paper. So first definition that we gave is this class of programs. So we fix the abstraction, and we consider all the programs such that the analysis of those programs on this fixed abstract domain are the best ones. And so for the whole set of programs, we have a kind of partition: the programs whose analysis is the BCA, and the programs whose analysis is not the BCA. This is for any set of abstract preconditions, but we can also focus on a given abstract precondition, A, and so we have this corresponding partition of the set of programs, those which are locally best for the input A, and those which are not. Okay, and so for these two classes of programs, we studied their structural and computability properties as, let's say, a preliminary step before providing proofs that the program has the best analysis in a given domain. So first observation is the following. So this property is not trivial, it's not straightforward, let's say, because triviality is a notion that we use for the domain. When a domain is trivial, well, a domain is trivial when either it is the concrete domain, so it coincides with the concrete domain, so it's a different representation of the full set of concrete values, or it just represents that don't know information, so just the top information. In that case, So it's the corner case of abstract interpretation, the total abstraction and the no abstraction at all. The domain is called trivial domain. So why this? Because in this case, it happens that we have this result, that for when it happens that the BCA class for a given abstraction coincides with the whole set of programs, well, this happens if and only if that domain, that abstraction is trivial. And so this resembles a little bit the well-known, there is a flavor similar to the well-known Rice theorem in computability. Okay, this is for the global best notion, but the same happens for the local BCA. So when we focus on a given precondition A ranging in our domain A. And so this happens that this is the full set of programs if and only if the domain is trivial. Then the second question that we faced is, okay, so can we transform a program, let's say syntactically and in an effective way to achieve this property of having the best analysis? And the answer is no. And what is precisely what we want to do with this transformation? So we fix the abstraction, we fix the after precondition A, and then what we show that there is no transformation, so no effective, computable, terminating transformation of programs, such that you preserve, of course, the behavior of the program. So in that input, for that specific A, and what you get is a transformer program that satisfies the BCA for that input. Well, this cannot be done. This cannot be done. So the answer is negative. Third point, okay, so we do analysis, and then we have a corresponding notion of equivalence driven by that analysis on that domain. So two programs are equivalent when they have the same analysis, and what we define to be an extensional abstract equivalence when this preserves the concrete behavior of programs. So we say that this abstract equivalence is extensional when for two programs which have the same semantics, the analysis is the same. Well, what it happens is that this happens, this extensionality property, if and only if the best analysis, the programs having the best analysis is the full set of programs, and this happens if and only if the abstract domain is trivial. Actually, it's just the concrete domain because the don't know domain is excluded in this result. Fourth result, negative result, impossibility result, the BCA is not a recursive property. So if we consider a non-trivial abstraction, what happens is that both the global and the local version of the BCA set of programs is not recursive. And so what does it mean? It means that for these two checks, for these two decision question, is P has a best analysis on a given domain A, or locally for a given abstract input, these two questions cannot be decided. There is no algorithm for them. Okay, second question that I mentioned before. Can we transform the abstraction? And the answer is no. So transform the abstraction means that can we minimally transform the domain either by refinement or by simplification? So more precisely, the question is, does there exist the least domain refinement of a given domain A such that we can achieve the best analysis on that domain for the given program P, either globally or locally? And on the other way, so can we simplify in a minimal way so there is the greatest domain abstraction for achieving the BCA? And the answer is simply no. The details are not given here in this talk. Okay, so far just negative answers. So what can be done in positive for this BCA property? So what we defined is a notion of BCA triple. So we have a program. So the abstraction is fixed. we have a program, we have an abstract precondition, we have an abstract postcondition, and the meaning of these triples, so the notion of validity is the following. So the analysis of P from the precondition A is B, okay, quite expected, but this analysis is the best you can do. Okay, so what we want to do is to prove these triples, to have a system for proving the validity of this triple. Let me give you an example. So it's the usual +1, -1. So for this triple, you see the precondition is being positive and the postcondition is being positive. This is not a valid triple. Why? Because this is not an analysis. Okay, because if you analyze this program, starting from the positive information, then you get here positive and then not negative. So this is not an analysis. On the other hand, here you have a precondition which is positive. The postcondition is non-negative. This is not the case. This is not a valid triple because this is not the best you can do. On the other hand, if you start instead from the precondition which is non-negative, non-negative, then this is a valid triple when you put as postcondition non-negative. Because, yes, this is the analysis and this is the best you can do. Okay, so what we have a system for proving this triple. So I provide an example for explaining at least a little bit the rules of our system. And okay, so what we want to prove is that for this loop, where the guard is x is greater than 0, and then we do -1, starting from the abstract precondition. Okay, so we are always speaking about the sign domain. Starting with the abstract precondition, which is being positive, the invariant is non-negative. Okay. So a proof in this system, in a way, it's an analysis of the program starting from this precondition, together with a proof that what we are doing, this analysis, is the best we can do. If the analysis, of course, succeeds, if the proof succeeds. So we start from the basic transfer function, which are this Boolean guard and this assignment. So the precondition here is positive, so here we are positive. This is the best we can do. Here we are positive -1, and so here you are positive or 0. And this is the best we can do. And so for the basic commands, the two axioms that we have is, yes, the postcondition is always the best we can do. It's the BCA. Good. Then we want to join them, because these two basic commands are composed with sequential composition. And we can do that because for the first, what holds is the gamma completeness of that test. Gamma completeness means that you take a guy which is in the domain and you have as postcondition a guy in the domain. And here this happens because if you filter x is greater than 0 with x is greater than 0, you get x is greater than 0. And so this is a sufficient condition for composing the two triples. And so here gamma completeness holds, and so you can join this with this, you can compose, and you get this. And this is a valid triple. Okay, let's go on. Let me skip the general rule. So now we want to take into account iteration, the loop. So the rule for iteration is the following. Basically, is the rule for having an abstract invariant, which is the best abstract invariant. So as long as you find as postcondition a B, which is the best for one iteration, and this is an invariant, so B implies A, then A is the abstract invariant. Okay, so for what we have now, this cannot be done. This cannot be done because you see this Z being positive or equal to 0 does not imply being positive. So this is not an abstract invariant. So what can we do? Let's first weaken the precondition. How to weaken the precondition? So we have a weakening rule for the precondition, and this is the rule. The idea is that we can weaken a precondition A prime as long as the postcondition is still implied for the analysis. And so this is the case because if we analyze this body of the loop, starting from greater than 0, okay, we can imply, starting from greater than 0, greater than or equal to 0, we still imply this. And so we can weaken this greater than 0 to greater than or equal to 0. So now we have this triple, okay, using the rule of abstract invariant, okay. But this is not what we want because in our goal, we want to prove that the abstract precondition is greater than 0. And so now we have a second rule, which is a recursive rule for the invariant, because you see here we have the cleaning star here as a precondition. And the idea of this rule is that we can put here a different precondition A as long as you can reach the C after a finite number of application of the body. So if we start from A and we can reach C by preserving the best property, then this C can be weakened to A. Okay, so this is the case for our example, just with one iteration of the loop. And so, yes, this is the hypothesis that we satisfy. So in one iteration from greater than 0, we get greater than or equal to 0. And so we conclude here greater than 0. And so in the end, we did the proof. So the proof actually encodes two facts, that this is the analysis of this program starting from this precondition, and this abstract postcondition is the best analysis. Okay, so we have the rule for the choice, which is the expected one. And let me just mention that there is no weakening or straightening rule for the postcondition because we have an equality on the postcondition. We have an equality. And yes, this is our best effort that we put for proving properties of the BCA. Just for future work, just 20 seconds. So consider this little program, okay? So this little program can be viewed in two different ways, either putting the parentheses here on these two assignments, or putting the parentheses here. What is the difference? The difference is that here you have a BCA, here you have a BCA, and so you decompose the program into subprograms that satisfy the BCA. But while if you decompose the program that way, this is not true. And so the question is, can we break a program suitably in a way such that these subprograms satisfy the BCA? Thank you.
All right, thank you very much. We have maybe one quick question while the next speaker can prepare their laptop. Yes. There. Who is the next speaker?
This is maybe not a particularly bright question, but in our previous work we defined the notion of local completeness with respect to concrete points. Here you are considering local completeness with respect to abstract point.
No. So here, part of this system is proving that we are doing an analysis, and that's why the precondition. Yes.
But can it be recovered in the work?
No.
Do you have
No.
a microphone?
No.
I still need to knock.
Ah, the microphone is here.
All right, so let's thank our speaker again.